too compliant, it's because it's soft. When you say something is very stiff, it's because it's stiff, right? It's not compliant. So the opposite or the inverse of stiffness is going to be compliance. And when you relate strains to stresses, what you get in the middle is the compliance matrix. All right. Now that we have the compliance matrix, this is very useful because actually I like to come back and write this in terms of stiffness, not in terms of compliance. And if you remember a little bit from linear algebra, if I have a vector here and I have this compliance matrix D multiplied by a vector, if I wanted to get the inverse of this, or let me say in other words, if I want to get the stress as a function of a strain, what I have to do is I have to multiply the inverse of D on the left side of this compliance matrix, and the result of that is going to be a new matrix which is called C, and this one is the stiffness matrix. If you want to check what I'm going to write, you're welcome to do that, but we're not going to do it. You have to take the inverse of this matrix. You can do that with Wolfram alpha, for example, with all symbolical operations, and you get the answer. Yes?
Isn't it that when you multiply a matrix by its inverse, you get the identity matrix? I think there's not supposed to be a D second equation before the...
Correct. So, okay, let's do this step by step. Very well. So you multiply D times D. Here you get identity, and here you will get that. So thank you for catching that. I was trying to say some steps, and I did something wrong. So the inverse of D is going to be C. All right. So I was telling you that I'm not going to show that we're not going to do all that math because that doesn't make any sense now. I'm just going to write a solution to what C is. And now I'm going to have the sigmas as a function of the strains. And this matrix is going to look something like this. There's going to be a common factor. Now I'm not going to write inside the matrix because it's a common factor. I can take it outside. And remember, guys, that all these equations, I'm writing them again just because I find that a little more helpful to explain what's going on. But all of these are already in the notes, and you don't have to rewrite them again. But if you want to do it, you're more than welcome to do that. I actually encourage you to, even if you don't complete writing everything, that's fine. But at least for me, forcing myself to take notes sometimes forces me to pay attention to something. And if I don't take notes, I start to check my phone, I start to think on other things. But at least taking notes forces me to pay attention to what I'm listening to. But if you fall behind, don't worry, because all these equations are going to be in my notes. Okay. Almost done. All right, done. So this is the stiffness matrix. All of these things. And it relates stresses to strains in 3 dimensions. I can give you any strain here, and you can tell me now what the stresses are going to be. All of them. Normal stresses, shear stresses, anything. As long as you know what's going on here, now with this equation and with this matrix 6 by 6, you can get all the stresses. Not just in one direction, but in all directions. So let's see an application problem about how we can use these equations in order to solve a particular problem. And the first thing that we're going to do is to try to use this new theory that we have in order to predict what is horizontal stress. If you remember from the equations that we had before, there was no way for us to tell what horizontal stress was. We could compute vertical stress. We know what pore pressure is, but horizontal stress, we didn't know what that is. And now, with this new equation, we're going to get a solution for that. Okay, so what we're going to see is what is called a uniaxial strain stress path. And what that means is that we're going to see what are the stresses that are involved whenever I have a type of stress path in which, for example, if let's say that I'm offshore, okay? I'm offshore here, I'm running some seismic lines looking for oil, and here I have some sediments that get deposited into the seafloor. As time passes by, these layers get buried and get increasingly deeper, right? So this would be a typical sedimentary sequence, that I have layers and layers and layers of rock that get progressively buried with time. Well, in this type of system, a piece of rock that, for example, started somewhere over here, and after a long time, it is somewhere down here. In the absence of any tectonic plate movement that is either squeezing or extending these sediments, the same sediments are going to remain in the same vertical position. They are not going to go sideways, they are not going to stretch, they are not going to compact, and therefore, what probably here on the surface started as something that was very porous, as you add more and more load, let me do it with another color, it's going to change size, but it's going to change size mostly in just the vertical direction. Okay, this plot was not very good. Let me add the dash line. But what I'm meaning here is that there is only compaction in one dimension, in the vertical direction. Why? Because it's not extending, it's not getting shorter in lateral direction, and it's just getting shorter in the vertical direction. And let me add some axes over here. Let's say this is 1, this is 2, and this is 3. The result of this type of compaction is going to be that the strain in direction 1 is going to be equal to the strain in direction 2, and it's going to be equal to 0. Okay, here you cannot see direction 2, but the same thing is going on. This rock is just going down and getting deeper and just getting compacted in direction 3. But it's not suffering any change of strain in direction 1 or 2. So these two are 0. Epsilon 3 is not going to be 0. because it is getting compacted in vertical direction. And in addition, we're going to say that the strains that are related to shear are going to be equal to 0. Okay? So 0, 0. These conditions that I'm writing right over here, where there is no stretching in horizontal direction, is something that people in structural geology call it a tectonically passive environment. And in the absence of any significant tectonic plate movement, then I'm just going to have these conditions. And these two, let me just go one step further to what we're going to see next. Now these are 0, but sometimes they could not be 0. And these are what are called tectonic strains. And those are going to be in lateral direction. But now they are 0, okay? So, let's see what would be the result of putting all of these together into this equation. So, first of all the strains, we said, shear strains, here, right here, these are going to be 0. And since these are 0, all this part, I don't care about it, because all those are 0. I just care about the top part. So I'm just going to care about this section, okay? So let me rewrite those equations now for the top. Sigma 11, sigma 22, sigma 33. One plus this, one minus that. And since I just need the three top quantities, I'm just going to write a matrix 3 by 3. And now I'm going to add the conditions for uniaxial strain, which are horizontal directions are equal to 0. So therefore this one is going to be 0. Epsilon 2 is going to be 0 as well. And the only one which is not going to be 0 is epsilon 3. Okay, let's solve first for what would be the effective vertical stress according to this equation. So if I want to get the third element, I need to multiply the third column, the third row, times this vector. And as you can see here, these two are going to be Poisson ratio times 0 is 0, Poisson ratio times 0 is 0, and the only one which is going to be different than 0 is this one. And the result is going to be that sigma 33 is going to be this factor times the common factor that was outside the matrix times sigma 33. And this is the first equation that I want. Oh, there's a mistake here. Okay. So, just for a minute, think about that equation and let's think about, let me see where I have a clear version of that. Well, I think I don't, so I'm going to put this one. Okay. So look at this, epsilon 33, sigma 33, yeah, modulus. And now I'm telling you that I have sigma 33, epsilon 33, and I have something else relating those two. What is the difference? Is there something wrong here? Or what's going on? So with this new equation that I'm giving you right now, I'm telling you that there is a relationship between vertical stress and vertical strain, and it's not the Young modulus anymore. So what has changed in the new equation compared to the previous one? Which is a key assumption, which is something that I want you to remember very well. Any idea?
Is it that this one's confined?
This one is confined. The other one was not confined. The other one could expand to the sides. I applied the load and it was free to expand to the sides. No confinement at all. The new case, it's a case in which I'm deforming a solid. Try to do it 3D. And I apply a load. Sigma 3 in direction 3, but this one cannot expand to the sides. It just deforms in vertical direction. So, as a corollary of what we just said, without making any math, just by trying to think what's going on in here. This coefficient, all of that, is called M, and it's called constraint modulus. If I were to compare the Young modulus and the constraint modulus, which one is going to be larger? Constraint modulus or Young modulus? What do you think? Well, let me bring that again, because I think it's useful to look at the two of them together. So, would it be harder to push something which is confined to the sides or which is not confined? The one which is? It's going to